Hi students, welcome to my YouTube channel. Today's topic is linear differential equation with constant coefficients. This is my lecture series for this chapter. So first, we'll see its definition. What is linear differential? A differential equation of order n is said to be linear if it is linear in the dependent variable y and the derivatives y dash, y double dash, dot dot dot, yn, meaning the first order, second order and nth order derivative of y, okay? So what is the general form of this linear differential equation? So the general form is of this type: a0 d and y dx to the power n plus a1 d to the power n minus 1 y dx to the power n minus 1 plus dot dot plus a n minus 1 dy dx plus a and y is equal to fx, where fx and the coefficients a0, a1, dot dot an are constants or functions of x assumed to be continuous, real valued on a real interval a comma b. Now see, these a 0, a 1, okay, these are constants, these are real numbers, okay, and they can also be functions, and its order is not order. Okay, this is a not order differential equation. It's written here not order linear differential equation. If we take the value of n as 2, then its highest order will be d2y dx2. Okay, then it will end here, meaning a0 d2y dx2 plus a1 dy dx is equal to something fx or some constant, whatever. Okay, this is the type of form it has. So here I have written a note. Now, if capital D denotes the differential operator d by dx, which is the operator, then equation 1, which was written as equation 1, can be written as what type? Like a 0 d to the power n plus a1 d to the power n minus 1 plus dot 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 a n minus 1 d plus a n whole into y, because there will be a y here too, meaning dy dx. How can we write dy dx? Capital D into small y, okay? Capital D into small y. How can we write d to y dx to capital D square into y? So for this operator, d dx is equal to capital D. So if we take y as common, if we put it here in the operator form and then take y as common, then it will be of this form, equal to fx. Now see, let's move to the next definition, homogeneous linear differential equation. So for a homogeneous linear differential equation, the right hand side of equation number 1 fx, okay, that it is written. Now if the right hand side of equation 1, that is fx is equal to 0, then equation 1 will be called homogeneous linear differential equation. Okay students, the if fx is equal to 0, then equation 1 becomes that equation number 1, its right hand side will be 0. Okay, now see, if a 0 is not equal to 0, then we can divide the coefficients of the entire differential equation in the second term, third term by a0, like d and y dx to the power n plus a1 by a0 into d to the power n minus 1 y dx to the power n minus 1 and so on, plus a n by a0 into y is equal to 0. Okay, so we have named a 1 by a 0 as P1, wrote a 2 by a 0 as P2, and a n by a 0 as Pn. Meaning, in short form, if we write all of them together, then Pi is equal to An by Ai, where I is equal to 1, 2, dot dot n. That is, if we write it in operator form, what will it be? It will be d to the power n y. So y is taken common at the end. P1 d to the power n minus 1, Pn minus 1d, Pn into y is equal to 0. Okay, let us write the homogeneous linear differential equation to this one. Since fx is 0 on the right hand side, it is homogeneous. Linear differential equation 2 in abridged form as L of y is equal to 0. Sorry, L of y, okay? L of y is equal to 0, meaning this operator, linear operator of y is equal to 0. where L of y is equal to d to the power n plus p1 d to the power n minus 1 plus pn minus 1 into d plus pn into y. We shall call L a linear differential operator. Okay? Okay, students. Now we'll look at the properties of the linear differential operator, the L operator that we wrote. A linear differential operator has the following two basic properties. One, L of Cy is equal to Cl of y. Okay? The properties that a linear transform has. So there are two properties of that type here as well. Now it will be C into L of y. That is, if we multiply a constant factor can be written outside the sign of the linear operator. Since why does this happen? We have also judged that L of Cy is equal to, if we put Cy here, C is a constant, it will come out. The derivative that occurs will be the derivative of y, like differential. N minus 1 times, so the derivative will be on y. C being a constant will come out. So ultimately we can write this in the comma L of y format. Similarly, this is the second property. The second property is what is L of y1 plus y2. Okay, it will be separated. L of y1 plus L of y2. That is a linear operator applied to the sum of the two functions y1 and y2. y1 and y2 is equal to the sum of results applying the same operator to each function separately. Since we've also judged this value of the operator L is y1 plus y2. When we differentiate this, we'll do it step by step, term wise. We'll differentiate the first term plus the second term, meaning the derivative of the first term is L of y1 and for the second term it will be L of y2. Now we'll look at a theorem here. Now if y1 and y2 are any two solutions of the equation, L of y is equal to this equation into y is equal to 0. Linear differential equation, homogeneous differential equation, okay? The right hand side is 0. Then c1y1 plus c2y2 is also a solution for any constant c1 and c2. Okay, this is how it is. This is very simple because y1 and y2 being solutions means L of y1 will be 0 and L of y2 will be 0. Now it is required to prove L of c1y1 plus c2y2 is equal to 0. So if we apply this, since L is a linear operator, so we can separate it as L of c1y1 plus L of c2y2, meaning c1 into ln of y1 plus c2 into ln of y2 is equal to 0 plus 0, which is 0. What we did earlier, log of le1, that was the first property, and log of le1 plus le2 equals log of le1 plus log of 2, those were the two properties. We can write them together as this type of property. L of c1y1 plus c2y2 equals c1 into L of y1 plus c2 into L of y2. If this is satisfied, then we can call it a linear operator. Okay, instead of those two properties, we can also test with just this one property. Now a note is written here. If y1, y2 up to yn are solutions of the equation L of y is equal to d to the power n plus p1 d to the power n minus 1 plus so on plus pn minus 1 d plus pn is equal to 0, then the linear combination, meaning the two solutions we had, y1 and y2, their linear combination was c1y1 plus c2y2. Here we have n solutions, okay? If we take the linear combination of n solutions, it will be in this format, c1y1 plus c2y2 plus so on plus cnyn, then this will be a solution of this, okay? So its proof will be of the same type. No problems there. Now look, now we should learn what a linearly dependent solution is and what a linearly independent solution is. Now what is a linearly dependent solution? The solutions y1, y2 up to yn are called linearly dependent if the Wronskian of y1, y2 up to yn is equal to 0. That is, this Wronskian, we can write it like this, and in its format y1 y2 comma dot dot yn is equal to 0. How do we define this? How do we define the Wronskian? Now where the Wronskian of y1 u2 dot dot un, how can we write this? Now the determinant of y1 y2 y3 dot dot yn, then its derivative will be taken for the first time of the first order, 1 dash a2 dash a3 dash dot dot an dash. It will continue like this. So there were n solutions here, okay? We are testing n solutions. So the derivative will be up to n minus 1. That means it won't be the north derivative, it will be the derivative before that. Since there are n solutions, therefore the derivative will be up to n minus 1. y1 n minus 1 y2 n minus 1, y3 n minus 1, dot dot yn n minus 1. So if we test the Wronskian of 2, the Wronskian of y1 comma y2, what will it be? Now the determinant of y1, y2, y1 dash, y2 dash. It will end here. Both, there'll be two rows and two columns. y1, y2, y1 dash, y2 dash when we have to find the Wronskian of y1, y2. Okay. Linearly independent solutions. The solutions y1, y2 dot dot yn are called linearly independent if the Wronskian of y1, comma y2 dot dot yn is not equal to 0. Okay, now what will we see? Now the solution of linear differential equations with constant coefficients. Okay students, the constants I mentioned here in a linear differential equation, these can be constants. These p1 dot dot pn minus 1 pn, these can be real numbers, meaning they can be constants and also functions. Okay, so here as well, what do we have? Where p1, p2 dot dot pn are all constants and fx is any function of x, it is called an LDE, a linear differential equation with constant coefficients. The solution of equation A is composed of two parts. If we find its solution, we have to find it in two parts, composed of two parts. Like part 1, in the first part we have to find the complementary function, and in the second part the particular integral is found. That means its general solution will be y is equal to the complementary function plus the particular integral. CF means complementary function, PI means particular integral. Now complementary functions in the case of a second order linear differential equation with constant coefficients, how do we find them? See, if we take a higher value for n, we can find it. But first, for the second order, how to find it? Then if n is equal to 3, how to find that? We'll talk about that later. We'll discuss it further. First, when n is equal to 2, its complementary function, let's see how to find it. So it's considered here, let the differential equation be given by d2 by dx2 p dy dx plus qy is equal to fx, where p, q are constants and fx is a function of x only. P, q are constants, okay students? Keep that in mind. Then the complementary function will be the solution of, what is the complementary function a solution of? It is the solution of the homogeneous equation. We will choose 0 on the right hand side. If it is 0, then there are no problems. If it is not 0, then we will take it as 0. Okay, this is the rule for finding the complementary function. We have to take the right hand side as 0. Okay, if y is equal to e to the power mx is a trial, if we test e to the power mx as a trial solution, so m is multiplied each time. First we get m e to the power mx, second it's m squared e to the power mx. This keeps repeating. So we'll write this as the trial solution, okay? Y equals e to the power mx. E to the power mx is obviously not equal to 0. Then, since we took this as a trial solution, it means it will satisfy the equation here. So, differentiating it twice, we get m square into e to the power mx. Differentiating once, we get m into e to the power mx plus q into e to the power mx. Taking the terms common, we get m square plus pm plus q into e to the power mx equals 0. Taking it common, since e to the power mx is not equal to 0, it means m square plus pm plus q equals 0. E to the power mx is not equal to 0, so that means m square plus pn plus q equals 0. Okay, now see, this is a quadratic equation which will have two solutions, two roots or two solutions, which is called the auxiliary equation. This type of equation that we get in m, a function of m, what will we call it? The auxiliary equation, okay? In short form, AE, and which is a second degree polynomial equation in M. It has two roots. So the roots it has, there'll be different types of roots, and for those there'll be different types of complementary functions. For example, if the value of M is real. Case 1. When the two roots of 3 are real and unequal, say m1 and m2, where m1 is not equal to m2, then what will the complementary function be? Then both constants will appear, okay? What will appear in the general complementary function? Both constants, c1 into e to the power m1x plus c2 into e to the power m2x, where c1 and c2 are two constants. In case 2, when the roots of 3 are real and equal, say m1 and m1, okay students, then what will the complementary function be? See, c1 into e to the power m1x plus c2 into e to the power m1x. Leave the x here. I multiplied by x here. Why did I do that? I will tell you. it will be a solution like the previous one, that type of solution, c1 into e to the power m1x plus c2 into e to the power, here m2, there m2, here it won't be m2, it will be m1x c2 into e to the power m1x when m1 equals m1, meaning both roots are equal. But what's the issue? If we have e to the power m1x here and also there, what happens? Both solutions become dependent. So what do we have to do? We have to make it independent. For independence, what will we do? We will multiply it by the smallest power of x, okay? If we take the lowest power of x here, we will multiply by x. That means first we will multiply by x. If after multiplying by x it is still linearly dependent, then we will take a higher power of x, like x square, like this. Then if it is still dependent after multiplying by x square, we will multiply by x cube. But if we have e to the power m1, c1 into e to the power m1x plus c2 into e to the power m1x, and if we multiply by x here, then this e to the power m1x and this solution y1 and this y2 x into e to the power m1x both will become independent. Okay students? So if we take e to the power m1x as common, then what will the solution be? c1 plus c2x into e to the power m1x. Okay, this is how we will remember it. Why did we multiply by x? We multiplied because we have to make it independent. Case 3. When two roots of 3 are complex, say m equals alpha plus minus I beta, I equals root over minus 1, and alpha and beta are two real numbers, then what will be its solution? See, we take alpha plus I beta. When there are complex numbers, they occur in conjugate pairs because its constants, I mean the coefficients of the equation, were real. If there are real coefficients, then the complex roots will occur in conjugate pairs, okay? So what will be the complementary function? C1, think of alpha plus I beta as M1 and alpha minus I beta as M2. So what will be its solution? C1 into e to the power alpha plus I beta into x plus c2 e to the power alpha minus I beta into x. See, we can write it like this. C1 into e to the power alpha x into e to the power I beta x plus c2 into e to the power alpha x into e to the power minus I beta x. We'll take e to the power alpha x as common. C1 e to the power I beta x plus c2 e to the power minus I beta x. E to the power alpha x into c1 cos beta x plus I sin beta x, which is the value of e to the power I beta x. What is the value of e to the power minus I beta x? C2 into cos beta x minus I sin beta x. Okay. If we take cos beta x as common, then c1 plus c2 into cos beta x. If we take sin beta x as common, then it stands v1 minus I c2 into sin beta x. Taken as common, okay? See this. C1 plus C2 into cos beta x plus I into C1 minus C2 sin beta x. We write C1 plus C2 as its new constant, capital A into cos beta x, plus I into, we write this also as a new constant, capital B into sin beta x. Meaning the value of A is this one and the value of B is I into C1 minus C2. So that means the solution we got when it is a complex conjugate, then the complementary function for that is e to the power alpha x into a cos beta x plus b sin beta x. Okay students, we are finishing here today. In the next class, we will discuss the complementary function for the third order linear differential equation. Thank you for watching my video. If you like the video, please share it with your friends. Thank you. Thank you.